my name is Georgia Drulinou. I am a PhD student at the University of Crete. In this talk, I will present our work on exploring RDFS knowledge base using summaries. This is a joint work with RINOS Slovenia and Dimitris Plexousakis from Foundation for Research and Technology and Kostas Emfanidis from University of Tampere. As you already know, there is an explosion growth of the semantic web and the associated link of the data led to enormous amount of widely available RDF datasets. Moreover, these datasets often have extremely complex schema and contain huge amounts of information which are difficult to comprehend, limiting the exploration of this information. As a result, there is an increasing need to develop methods and tools that facilitate the quick understanding and exploration of these data sources. To this direction, ontology summarization tries to deal with this problem. Ontology summarization is a procedure that tries to produce an abridged version of the original source, highlights the most important information, reducing the size and the complexity. In this figure, we can see the Wikipedia version 3.8 as a graph, and it is obvious that it is difficult to understand the content of this knowledge base. Even if we highlight the most representative nodes, the red ones, according to some important measures, the problem persists. So now consider selecting the top K most representative nodes and construct and connect them in order to construct a summary, as we can see in the right figure. Here we can have a better view of the content of the Wikipedia, but still user could find this presented information overwhelming. And maybe he would like to focus only to 10 or 7 nodes, or she might want more detailed information not on the whole graph, but on the selected subset of it. So the static summaries aren't adequate. So now we can talk about dynamic exploration over summaries. In this work, we view an RDF data as two distinct and interconnected graphs, the schema and the instance graph. In the left, we can see a schema graph and specifically a part of the loop ontology. The nodes depict classes and the edges are properties. And on the other side, the instance graph contains all individuals and the instantiation of the schema properties. So let's see in more details how we can generate a schema summary for a dataset. Firstly, we should assess the importance of each schema node in order to select the top K most important nodes. So we examine a variety of centrality measures. Between us is a measure that have already examined our previous work and behaves quite well since it produces summaries with better quality. And in this work, we explore two additional well-known measures, the page rank and the hits. Since these measures have been developed for generic graph, we adapt them to be used for RDFS graph using instances. So the adapted important measure for each node is the sum of the normalized values of the important measures and the instances. After that, we rank the schema nodes and select the top K nodes according to the size of the summary. Since our goal is to construct a summary graph, a subgraph of the original schema, we should connect the selected nodes using the graph Steiner tree. This algorithm achieves to select the paths that introduce the minimum number of additional nodes to the final summary. However, this procedure is very expensive, so we use an approximation of the Steiner tree. Now we have described how we construct the summaries. Let's see how we can dynamically explore a knowledge base using these summaries. In this work, we suggest two exploratory operators, the extend and the zoom. The extend operator focuses on a specific subgraph of the summary and try to add more detailed information about the selected area. The extend operation takes as an input a part of the summary schema, for example, the blue node, and identifies other nodes that are dependent on the selected one. and in order to construct the final extended summary. While the zoom operator focuses on the whole summary, increase or reduce in this simple example the information included in the summary. But let's see in more details each operator. As I mentioned before, the extend operator takes as an input a part of the summary schema and identifies other nodes that are dependent on the extended one. But what the term dependence means to us is a combination of things. So, for example, assume the selected node person and the node student ID. Firstly, we want to examine how close these two nodes are. The node student ID is close enough to person since each person has a unique ID. Meaning that infrequent connections between the classes are more informative than frequent ones. This is how we call it cardinality closeness. Secondly, the importance of the node takes place in the estimation of the dependence. And finally, as the distance grows, the dependence becomes smaller. According to this dependent measure, we can select the most dependent nodes for a specific subset of the summary. In the following example, for simplicity, our subset contains only one node, the person, and the red nodes represent the most dependent nodes. The next step is to find how to connect the selected nodes with the summary. Our goal is to find the paths with a minimum number of added nodes, connecting the selected ones with the summary. We have examined three algorithms for this purpose: the chains, the shortest path, and the dependence path. The chains algorithm is an approximation of Steiner tree, starts from a single node, and at each round extends the graph by a node that is nearest of the nodes that already exist in the graph. So after this procedure, the final extended summary graph is constructed. In contrast to the chains algorithm, in the shortest path algorithm, we maintain the connections in the existing summary, and we try to connect the selected nodes with the nodes of the existing summary, finding the shortest path. The third algorithm, the dependence path algorithm, also maintains the connection in the summary as the shortest path algorithm, but the difference here is that we find the shortest path between the node selected, for extent, the person in this case, and with the node selected based on the dependence, that is the red one. Now the zoom operator exploits the schema graph as a whole. We introduce the zoom in and the zoom out operator. The zoom in operator removes the less important nodes in the summary and the corresponding connections. And to link the remaining nodes, if it's necessary, we apply the chains algorithm. The zoom out operator adds the next k most important nodes in the example, adds the next most important nodes from the schema that are not included already in the summary, and link them with the existing summary using either chains or shortest path. Okay, to evaluate all approach, we use the version 3.8 of Wikipedia. It contains 359 classes, 1,323 properties, and 400 million triples, and more than 2.3 million instances. Moreover, we use a query log containing 50,000 queries provided by the Wikipedia SparkQL endpoint for the corresponding version from a specific period of time. Our goal is to assess the percentage of the queries that can be answered totally by using the generate schema summary and the corresponding instances. So this is our evaluation measure, the query coverage. Regarding the zoom out operator, we evaluate the average coverage for all queries for chains and shortest path, and for all centrality measures between hints and page rank, that depicted in each bar. As a baseline, the blue bar, we randomly selected nodes from the schema graph, connecting them with the corresponding measures. In essence, an average coverage of 70% means on average that 70% of the queries can be answered only by using summary in the corresponding instances. In this figure, we start from a summary containing 10% of the initial schema, and we zoom out progressively by 10% until reach the 40% of the schema. As we can observe, as the percentage of the summary increase, more queries are covered by the resulting summary. Hits and betweeners perform better, competing each other, and betweeners perform better from 20% zoom out and on. It is nice to mention that betweeners achieve coverage something around 65% for 20% summary. That's an impressive number for us. And moreover, teens and shortest path retain same quality and with shortest path slightly better. About the extended operation, since now we are interested to get information relevant to a particular selected nodes and not for the whole schema, we will calculate the average coverage for queries, included only classes from the selected extended part. More precisely, in our experiments, we extend each summary node and present results for the average. Starting again for a summary, 10% and extend for 10% to 40. We examine all the algorithms, and as we can see, the shortest path algorithm provides the best results in all cases, followed by teens, and the PageRank presents the best coverage, around 59%, while hits follow with coverage around 65%. All measures and the algorithms are available in the RDF Digest Plus system. An instance of this system is shown in this slide. Remember to visit us tomorrow at demo session and play with RDF Digest. And to sum up, in this work we introduce two operators, zoom and extend, in order to achieve an effective exploration of datasets using summaries. In the future work, our goal is to exploit summaries for approximate query answering and study how the extend and the zoom operators can use to this direction. Thank you for your attention.
Okay, great. Thanks, Georgia. Questions from the audience?
Sorry, I can't hear you.
How about user studies? Do you have anything contemplated for that?
Do you mean about the related work?
No, I'm saying, I'm assuming that this approach is eventually to help a user with a tool to actually understand. So how about...
No, I use only queries that represent the preference of a user in order to explore a data set. So it is the same for us.
I mean, I don't know the details for sure, but I think a lot of the query logs of DBpedia is also not, it's probably machine generated, so I'm not sure. So interested is how much are you covering, which is something that comes from a machine, a template type queries, or actual intentions of human beings who wrote the queries. So I guess that would be interesting to
yes,
understand.
it is interesting to also use users to evaluate our data except of the queries.
Well, please.
I'm going to ask the question about the user studies again. So at the end of the day, these summaries should be consumed by human beings. Is that understanding correctly? Yes?
Yeah.
So how do you know that the summaries are in any way good unless you have people try and use them? I mean, I understand what you've done is you've checked whether the summaries are able to represent the queries, check. But Now, the next question is, will a human being actually understand them? And don't you need to use user studies to ascertain that?
Yes, but users construct queries because they want something. They ask a database about something, and a query can express what a user wants to learn and explore in a data set.
Yes, but what you've constructed is a language to express queries, right, based on summaries. It is unclear whether people actually understand the language, and the only way to find that out is tested with people.
Yeah, you're right. Maybe in the future work we are also examining this part.
Other questions? Then I will ask one. So your summarization is at schema level, right? Do you think that it would be possible to extend or to have summarization at instance level?
Yes, we construct summaries using also instances, but we present only the schema. But of course, in our steps, we examine to summarize instances and also to expand the zoom and the extend operator on the instant level.
Another question, Matteo.
So the original schema graph, the connections between the concepts by means of properties, are they derived from the ontology from the schema, or did you also check into the data? Because like in many knowledge bases, there are several connections that are not represented into the ontology.
Summaries are a subgraph of the original schema, so we use the connections that the schema already has in order to connect the most important nodes according to centrality measures that I presented. So it's a subgraph. We don't create something else.
Okay, thank you.
Okay. Thanks a lot again to Georgia. So coming up next is Maurizio, one of the papers that has the most interesting title, What is the cube root of 27? I think I used to know the answer, but maybe now you will tell me how to remind it.
Okay, so hi everyone. This is a joint work with my student Mattia Zeni, and okay, so since you, let me see if I. Okay, so you like the title. So can you answer this question? What is the cube root of the max between 20 and 27? Can anyone answer this question? Okay. He was correct, 3. So, of course, it's easy for us. And also, writing a program that can answer this question is one-liner, no? Print 3. But we address the problem of answering this kind of question, which is a question-answering problem, of course, but not the typical one, the usual one. In fact, in this case, we cannot answer this question with usual factual question answering. For example, the usual question answer is like, what is the capital of Italy, or things like this. So you look up for results in a data set or in a corpora. And even advanced data querying is not enough because the answer is not in your data set. In this case, I mean, for this kind of questions, you must run some code to have the answer. And for example, if you use Java, we can run this simple program, okay? And what we did, of course, there are other kind of similar questions that we addressed, like convert my string to uppercase, or what is the size of ABCD, so the size of a string. So, of course, we are focusing on simple questions related to coding, basically. But the approach is more general, so we can also apply it to other applications. And so, what's the idea behind the approach that we used? We divided this problem, so the one of answering natural language questions that require running code, into 2 subproblems. One is providing a semantic representation of the object-oriented source code. So we need to represent in a structured way the code. And the other sub-problem, let's say, is the question answering over the resulting knowledge base. So first we construct this knowledge base, and then we query it. So regarding the first part, it was addressed in a previous paper that we presented last year in Vienna at ISWIC. In fact, we constructed code ontology, which is an ontology over object-oriented programming, describing object-oriented source code, and we also developed a parser that is able to analyze Java source code and generate RDF triples using the code ontology. Exactly. So, of course, it's important to understand how it works, because all the question answering system is made on top of this. So how code ontology works? Basically, given some source code, like the one on top, it's a simple code. You see, it's a class example with a method main, so it's a hello world program. And given this simple source code, code ontology parser provides or output this graph. And in this graph, you can see that there is a node representing the Java class, and also with a property as method and another node that represents the main method. And this main method also has returning type, etc., and also information about the comment, the natural language comment that represent in natural language what the method does. And also by using tag.me, we can also extract from the comments, from the text comments, other information, like basically we create links with DBpedia by using a tag.me tagger. So, for example, we can see that there are a node, a relation with the hello world program resource in DBpedia. So we start from this information, from this graph, and this is actually available online freely. We basically run code ontology parser over OpenJDK8, and so we produce a big data set. It's 2,500,000 RDF triples over OpenJDK. So, of course, it's easy to query this graph with Sparkle, and we can, of course, run this query like find me all the methods with a parameter that has a type double, and it's associated with the DBpedia cube root. So with Sparkle, we can answer, by using code ontology, the initial question and find a number of methods that match this description, let's say, these constraints. But we want to answer these questions and finding the right methods by just typing a natural language question. So what is the cube root of 27? So we splitted this again. We did it on top of code ontology. So eventually we query with Sparkle the graph. But we focused first on a simpler problem that we call the coarse-grained approach. In this simpler problem, we focus only on natural language sentences that corresponds to the execution of one single method. So it's a simpler problem, let's say. And then on top of it, we construct the final system. So the simpler problem, in the simple problem, we have a natural language specification. In this case, it's compute the cube root. That's a string. And then we have a list of parameters. So the question is not just a natural language question, it's somewhat structured. So we have a list of parameters, input parameters, and also we provide the type, the return type. So in this case, double. And this coarse-grained approach is interesting per se because there are applications of this task, actually. For example, if you want to provide some tools for the developer, so inside the integrated development environment, you want to have some tools to help the developer. So this is interesting per se. And how it works? Basically, it runs a Sparkle query constraining the results to have this kind of types. And then that's the interesting part, we need to rank the results because some of them are not the right answer. For example, also square root is somewhat related to this query. But of course, we are not looking for square root, we are looking for cube root. So we have a ranking system of these results. And then, of course, hopefully, if it works correctly, the one with the higher score is the method that we need to run in order to get the right answer. So how we approach the ranking problem? It's actually, we try to match all the textual information in the source code with the natural language specification of the query. For example, so one scoring method is to use the edit distance. So basically, it's a syntactic feature, of course. So we compare the edit distance of the description of a method and with the description of the query. So of course, edit distance is one measure. Other two measures are the n-gram overlap between the name of the method and the query, or the description of the method and the query, the class method and the query. And then we also use the semantic features. So we compare compare the question, natural language specification, and the method description using word embeddings. We just used the pre-trained Google News word embeddings. And also we exploit the DBpedia links that we extracted in code ontology. So we try to tag also the natural language specification of the query, and we see how many, basically how many, the ratio of the number of matching tags. Okay, then we constructed, we build it's a new problem, so we had to build a benchmark, and we have exploited Stack Overflow that contains a number of questions. Of course, we filter out all the questions that cannot be answered by running only one Java method. And for the other ones, the most popular questions, we get the result, the answer provided by Stack Overflow. And we also add other answers, because in many cases, like convert a string to an integer, of course, Stack Overflow provides one answer, but there are other equally correct answers. So that's how we constructed the benchmark. And we can see that every measure that we used, all of them, both the syntactic ones and the semantic features, they help in reaching a somewhat surprising precision, because 90% it's more than I expected actually at the beginning. So, of course, this is the coarse-grained problem. So we provide a natural language specification of the query, and also we provide separately the inputs and the type of expected output. And that's the first part. Then, on top of this, we constructed the final system, let's say, the one focusing on having only one string as input, which is the natural language question. And we answered this, we approached this by exploiting the previous approach. So in order to solve, let's say, the final graded approach, we exploited the coarse-grained approach. How we do this? We run the natural language questions against we perform basically dependency parsing, which is something that is provided by the Stanford NLP library. And so we get a graph, basically, this graph that you can see. This is the first step. Then that's a challenging problem. We try to transform this graph into a tree, and the tree will be the execution code, basically. So how can we do it? So the output that we want to have at this stage of our system is this one. So given the natural language question, we want to have this tree. And of course, we start by transforming the initial graph into a tree. So we label all the leaves with this kind of yellow tag, and all the other nodes with a green tag. But then, of course, it's not this. It will be a messy tree, okay, with many unuseful nodes and things like this. So we need to transform the tree into the initial tree provided by dependency analysis into something that we can run. So, and of course, we want also match. For example, we want to match max with a Java function that exploits, that computes the max, and same for the cube root. So we want to maximize the score of all the method calls. And another constraint that we have is that the output of a leaf or a middle node should be compatible with the input type of the other node on top of it. So, of course, the result of max should be compatible with the input of the cube root function. So the types must be, of course, compatible. Okay, so this is what it happens, that once we have a graph like this, and these are strings, basically, extracted from the initial question, we need to match against and find the correct method. This is done by using the previous approach, the coarse-grained approach. And as I said, there is a ranking problem, but in this case, it's a global ranking problem, because we want to match, we want to find the higher score among all the combinations. And of course, this is in terms of the space that we want to visit is quite large. So we approached it in a grid with a grid algorithm. And okay, so we perform a greedy search also because, as I said, there are nodes, there are problems with the graph extracted by using the Stanford dependency parsing. And so what we did, basically what we do is we transform the tree by merging nodes. For example, cube root. Okay, at the beginning there are two nodes, and then we create a node that is labeled only cube root. And so I'm running out of time, right? Okay, so I will go to so we transform this tree into a simple one. And of course, we weight all the edits negatively, so we don't want to change too much the graph. And finally, so we have a 91% of precision, which is much better than the only system that we found that we can compare against, which is Wolfram Alpha. It's a closed system. And so we are pretty happy with the results. Of course, I need to go faster because, sorry. Okay, and of course, if someone of you want to join us, we are running some experiments, so if you want to test it. Thank you.
So questions? Ooh, how many questions? Let's go there.
Thank you for your talk. Can you give a little bit more of details on how do you actually map the name of the method to what actually the method does? I mean, how do you figure that out? Because just by looking at the title of the functions of the method, I don't see how that can be done in a very clearly manner.
Yeah, basically we match the description, the natural language description of a method, also the name and the description of the class in which that method appears, against the question. And I'm also surprised that it's working pretty well. And of course, we focus. By the way, in these experiments we are focusing on something about Java Lang package. So we are working on strings and numbers. So it's limited in scope. But the approach works I mean, you can provide any Java code. For example, I remember a demo by IBM Watson, and it was like, it was like a picture of a car, and you can write something like turn on the lights or turn on the radio. And you can use this approach as well, because basically you are running something. So if you have a description of a method that say, this method turns on the lights of your car, you can use the same approach, basically. And also, in order to answer your question, we are also using word embeddings, so you don't have to use the exact words, of course. It's a semantic comparison, okay?
So I have two short questions. Question number one is using ontologies to analyze code predates the semantic web by quite a bit. Prem Devambu had the first ontology on code, more than 2 decades ago. So how does your work relate to that? And then secondly, people in the software engineering community have also used NLP tools to query code and get feedback and answers back on code also for at least a decade worth of work. How does your work relate to work there? So Wolfram Alpha is one thing, but there's been research work published in software engineering on that topic. How does your work relate to these efforts?
Actually, we also wrote a review paper, and we compare. I mean, we didn't find, if you know about it, we didn't find any paper working exactly on this problem, first of all. We only found systems that address this problem. One is Wolfram Alpha, which is very well known, but at least in this subset of problem, we can beat it. We perform better. And also, for example, also Google tried to address some, of course, it's not the main core of its business, but it performs some computation. For example, you can ask Google, what is the cube root of 27? And it answers 3. So that's another system that we may compare against. But, of course, if you provide some more complex question, it doesn't work. But even simpler ones, like increment 2, it doesn't work. So compared against these systems, I think it's a novel contribution. But of course, I'm not an expert in the field of software engineering, but all the papers I found there, they were not able to provide an answer to questions like this.
Yeah, hi. Thanks for the talk. I really enjoy the code ontology. I'm just a little bit confused, though, about your intent with this question answering system. So, converting the open SDK, the Java 8 SDK, into an ontology and trying to use it as a question answering system would seem to be a good idea if I wanted to ask to find out like what data structure I want to use in my code, right? This doesn't seem like the best solution for I want to do some operation on some number, or I have a question about how to get a cube root. It seems like that might be the only use case for something like this. I really can't think of any other thing that I would do with Java to ask a generic question.
I totally agree with you. I think it's a good title for a paper, at least according to Irene, and because it's a simple use case. Maybe it's not very useful for the real application, but it's something that it's easy to explain. But as I said, you can use the very same approach to very different scenarios. Like if you think about Alexa, okay, how does it work? You perform a natural language question, and it does something, okay? Please play Yellow Submarine by the Beatles, okay? So that's actually, it's the same problem. Of course, we didn't compare against Alexa yet, but what I'm saying is that there are many applications, very different from computing the cube root, but the approach, the system is, and the task, the question answering task is the same. So I think, I'm not sure if I'm answering your, okay?
Thanks a lot, Maurizio.
Thank you.
Okay, next on stage is Jose, and again, it's about having too much data and having to deal with it. So this is about face of the browsing, and the system Grapha. So, Jose, please.
All right, I'm going to present Grapha, scalable faceted browsing for RDF graph. So with a brief introduction, we have a lot of RDF knowledge bases, which contain information about millions of resources, like Wikidata, Diego, DVpedia. For example, in Wikidata, we have the following structure, where a resource has an identifier, a label, a description, aliases, and properties and values. And the standard for querying this kind of data is Sparkle. So a query in Sparkle looks like this, but an average user is too complex writing a query like this. So, a user in the internet is more familiarized with faster browsing, which he can look for different resources and apply filters or facets to find their desired result. And there are some faceted browsing interface for RDF, but we tried to load old Wikidata, and they didn't work. So current RDF faceted browsing interface does not support datasets large and diverse like Wikidata. And trying to use Sparkle for this kind of problem, queries look like this. And this kind of query could take more than 20 seconds for these datasets. So Sparkle is not a viable option either. So our main objective is to create an interactive faster browsing interface over large-scale and diverse RDF datasets, but we need to use appropriate techniques to store and query the data. And also, we want to offer to the users, not to ask for the users to have a lot of knowledge in semantic web, and keep interactive runtimes, so we don't want to wait more than a couple of seconds for get the results. And we also don't want to offer to the user facets that would produce empty results. For example, if we are looking for male people, the facet for first lady is not a valid facet, so it shouldn't appear in the options. So the expressivity of the system, we want to keep this interaction, so we can start a session by a keyword or selecting a type, and then we get a first result set, and then we can add facets to get a new result set and keep going until we find what we want. The operations of this system, we have keyword search, type selection, and facet selection. And in this case, faceted browsing will be, we will start with a keyword or type selection, kappa or tau, and then we apply the facet select function multiple times. For example, if we look for lakes in Cameroon, we start with the type lake, and then we add the facet country Cameroon. Or for male people in the United States, we start with type person, then gender male, and then country United States. And the facets are commutative, so we can change the order of the facets. So we can start with a naive system. We use the Wikidata Trusty dump from September last year, which contain around 75 millions of resources. And we store the data on custom Lucene indexes. And I don't know if you remember, but we showed this Sparkle query before. So I don't know if someone can say what does this query does, but we want a system where we can search this information like this. So the answer is lighthouses in Norway. So to the right, we have the results, and to the left, we look the type and facets and all the possible properties for continuing the browsing session. However, this naive implementation can take a lot of time to show the results. For example, for type human, it takes more than 2 minutes, and the results are more than 2 million. But so this approach is slow, but the problem is not only the type selection, because we can have more facets. For example, this query can take 1 minute, and we have type human and 2 facets, gender male and country United States. And we still have about 300,000 results. So we need to some way optimize the system. And the approach is to cache the queries that will produce a lot of results. And we look for specific properties that produce a lot of results. So we make a graph of the ratio of values that would need to be cached with varying threshold. And we can see that the value stays the same at around 50,000 results, which represents 2% of all facets. So the queries can contain multiple facets. So we need a cache for storing the combination of facets. And the caching structure, we have all the queries with more than 50,000 results. And for each one, we need to store in a cache the properties and values for these queries. So we can look for the performance with using the caching techniques. And we can see that for loading the results page, we run 1,000 sessions starting with type human and select random facets until we get one result. To the right of the dash line is the queries that are cached, and to the left, the ones that are not cached. Note that the graph has the x-axis in log scale. So the results to the right, we're talking about million of results, and to the very left, there are less than 10 results. So we can see that for cache results, the times are below 1 second, and for non-cache queries, the times are usually below 2 seconds. And for the facet selection, all times are below half a second. But where is the price we are paying for these runtimes? So for the index creation, we take 5 days. Most of the time is used to create the caching, and the size of the index are around 7 gigabytes. And how does the users find the system? We compare the system with the Wikidata query helper. When you can select properties and values, and then it shows the results. So with 11 students of a semantic web course, we ask one of each to answer 5 queries in each system, and we record their answers and give us feedback of the system. And the results shows that the users has problems selecting the type, so it's not intuitive what a type is. So with this feedback, we improve the system, we improve the type selection, and we ask for the Wikidata community for their opinion of the system, and we gave them some questions, and we can see some strengths of the system, like the community find the system useful, and they think that offers something novel for querying the data. And we can see some mixed opinions in like the system is usable and easy to understand. And finally, we find that the system achieved the objective of providing a faster browsing interface for large and diverse RDF datasets. Caching results is time-consuming, but the runtimes are very good. And the future work for the system, we propose to improve the type selection interface, add support for data type value in the facets, like dates, support more complex queries in the system, like nest facets, and student the viability of the cache for even bigger datasets. So if you want to try the system, check out our demo tomorrow, D10, and we can try the system. Here's the link for if you want to try it now. Thank you.
Thanks a lot, Jose. So time for questions.
Yeah, thanks for the talk. So in many faceted browsing applications, the facets are open and they show the counts of the values that are the distinct values or the top 10 values for each facet. Does doing this add a lot of expense to the approach that you are following?
We want to show all possible facets, so we need to compute all of them. For example, if we are looking for occupation, we could try to display the top results, but there are a lot of possible values, and we want to show them all for the user to select. So that's why this approach looks. I don't know if that answered your question.
No. So like in the first one, located in administrative territorial entity, this facet would be open and it would show the counts of the different territories and so on for most facets that appear at the top so that the user gets an overview of the data set just by looking at the facets, and that's a very useful feature.
Okay. There are a lot of possible values, so we expect for the user to select one property to then show the results, because we don't want to load a lot of data immediately. That will take a lot of time, actually.
For the open facets, you mean you can just look at all the values available for that property? Or, so you can do this in the system as well. You can do either autocomplete on a string, or you can also see all the values possible for that property. Also, it's ranked, not by number, because number is bad in our experience. Case being, for example, countries. There's very few countries, but they're super important. So everything is ranked with page rank, and we try to do some ranking as well. We could display the counts, I guess, but we don't at the moment. The counts for the values.
Yeah.
You could do that. Yeah.
Questions?
Hi, so Very nice. So my question here is, so basically when you build the facet, you look into the data, right? So you cache all the data. So I just wonder, that's an open question. If you got a type, how more difficult would be to use like structural information about the properties? So for example, we know that for this type, there are those most frequent properties, and maybe you also know more or less the cardinalities, so you can guess that this is not like either one-to-one or one-to-many, but a few. So my question is, do you think that there's like that this could speed up a bit like the process for most frequent properties, or you just look at the data and that's fine?
We look for the data because we want to support diverse data sets. So there are a lot of types. There are above 1,000 types on all Wikidata. So we can select properties for each of one of those types, but that makes the system more specific for a type of data set, and we want to support the diversity of a data set. We don't want to limit the properties.
Okay, I'll take advantage of being chair to ask the last question, which is how robust is your system to incremental additional removal to the knowledge base? Do you need to re-index for 5 days everything, or can you just make the delta?
We need to re-index everything because we also do PageRank evaluation to determine relevance of the resources. So we need to re-index everything for a new data set.
Okay.
Yeah.
So next step is to do it incrementally, of course. So thanks a lot, Jose, again. So last but not least, we have Stefano, and Stefano is presenting a paper from the resources track, and is presented this data set of multi-domain interest from Twitter. So Stefano, the floor is yours.
Thank you for the introduction. So the title is less interesting than the cube square, but this is a resource paper. So we present a resource. We are going to talk about the accessibility of knowledge from certain communities and how maybe this resource can be useful also for the semantic web and linked open data communities. This is a joint work with Giorgia Di Tommaso, Giovanni Stilo, and Paola Velardi. We work in Sapienza, in Italy, Rome. So just to thanks the co-author. So what is Wikimeet? Is a data set, is a resource containing users from social network and their interests. Is a fresh data set because we made the crawling of the data in a time window from April to September 2017. And why this picture as a motivational picture? As I said, this handshake is a metaphoric representation of some interesting aspect, at least for us, which are going to be detailed later in this presentation. So the handshake metaphor is between communities that work in general fields of AI, and on the other side, we have the semantic web and the linked open data. So we see this as a collaboration. We see that this handshake can create a lot of interesting things. One side, people from this side, sorry for the repeating word side, the people of these communities benefits a lot from the knowledge that comes from that side. At least in the last year, these people realize we can inherit from that formal, well-defined amount of knowledge. But somehow the semantic web and the linked open data does not include, let's say, too much social aware data. So that's why we propose such a resource as Wikimeet. Wikimeet may help the building of semantic recommender systems, or could be a framework, inspire a framework to develop any social semantic aware system in this side of the handshake. So this is the motivational, the reason why we made this study. More in detail, I want to spend some few more words about what in fact it happened when we are doing some NLP task. Usually we have a set of observation, is a set of symbolic ideas. And what happened is whichever probabilistic or distributional or statistical model we apply in our task, we are going to predict only ID we observed in our initial set. But thanks to the addition of the linked open data cloud and the semantic web, of course, we can do more precise prediction of symbolic ID. We can more additionally predict unobserved entities. And moreover, what is very interesting, at least for us, is to open to semantically related facts and entities. So this is, in my opinion, why we are proposing this resource. So one side is our communities want to reach this cloud of data, and the only way is to inject the semantic space provided by the linked open data into our model. So, back into the resource, the Wikimeet is a multilingual resource. By now, we have only English and American speaker and Italian speaker, but it's very easily adaptable to any language. What we did, we started from a population of about 400,000 English speaker Twitter profile and around 25,000 Italian speaker Twitter profile. From these profiles, we identified interests of this population, and then we identified, let's say, a multi-domain set of interests. Interests could be people, so we, in fact, in the resource, we linked the interest we found to Wikipedia. So when we close the circle, we have that we not only identified people as interest, but they are artists, influencers, sports people, writers, politicians, journalists, and so on. What we also found on the interest of the Twitter population we selected are organizations. So you may have non-profit organization, news media, you can have companies, clubs, and so on. And so on also for the type of entities we found as interest. On Twitter you can find profiles or whatever, products, songs, events, and more and more and more and more. Additionally, we were searching for interest by looking at the text of certain posts. So we relied on some specific service user used to consume, like Goodreads, and we found on the tweets certain keyword to identify tweets that are saying, in fact, I'm reading this book, I'm watching a movie, I'm listening to a song. So the other kind of interest we selected are, in fact, books. And so by linking to Wikipedia, we obtain all the semantic space given by Wikipedia. Movies, so we rely on the IMDb service. And on music. So we use the Spotify automatic generated tweets. So I'm listening this song. Wikimedia is let's say, a large data set. So we started from this number of Twitter user profiles. This is the data model we designed. It's a very simple one. We model user using the SIOC class user account. We do model the follows relation. We do model the likes relation into an interest, and we do model the related match to a Wikipedia page, as well as interests are mapped into resources. So some numbers. From this sample of user of Twitter, we find out this number, so around 400,000 followees, having a number of followers greater than 40. So these two numbers comes together as the total amount of user account we have in our data set, and the corresponding follows relation. Moreover, we, as I told you, we link some of the following to Wikipedia, and so we were able to link about 60,000 followees, so interest into Wikipedia, with a precision of 90%. Let's say that this number are in fact coming from a final selection of a minimal precision in the linking phase. Then when we look at tweets, so we search for keyword to extract the fact that users are reading books, listening to music, or watching certain specific movies, we have this number of tweets we crawled from this entire population, and we have a total amount of around 2 million, 3 million tweets that are in fact having this keyword and references to IMDb, Goodreads, and Spotify services. And finally, from this number of tweets, we were able to link around 300,000 interests to Wikipedia with a very high precision, because this methodology look for certain specific keywords, so the ambiguity in the tweets are very low. To summarize, the dataset contains around 60,000 linked interests to Wikipedia coming from the following relation on the social network. We have a user average of 82 interests of this kind for each user in this dataset, and from tweets we obtain an average number of interests equal to 6. So you can have an average number of books and songs and movies together that is 6 per user. So just a taste of the methodology. As I told you, we started from Twitter profile. So we have looked up at, in the phase of linking, the followee So the interest expressing by the following relation, we look up, in fact, to the list of the people followed by a single user. And we identified what is the friend of a user. In this case, this user, this is an Italian student from our university, do follow 76 people. In particular, this student followed Katy Perry profile. And we identified this as this user is interested into Katy Perry. Then, if we look to the Katy Perry profile, the Katy Perry profile has different components. There is the name of the profile, there is the screen name of the profile, there is there is a description that in this case is empty. The description is a textual, is a piece of text where user usually writes some few words describing themselves. And then we may have a URL to an home page. So this is the information on the profile. And if we go to this link, if we go to Wikipedia, we have for Katy Perry this page, but we may have a lot of pages for Katy Perry. So, in fact, the linking phase aim is to disambiguate the previous Katy Perry, so this Katy Perry, into the set of candidates in Wikipedia. If you try to search John Williams on Wikipedia, there are more than 100 pages referring to people having the name John Williams. So 1 minute. Okay, I can go quickly. So we look at this Wikipedia page, we find relevant information that we can use again as a match for the Twitter profile. If we go, for example, to the home page expressed on the Wikipedia page and on the Twitter profile, we fall in this page where we can find some key information to match the profiles. In fact, we do a voting system on 3 different disambiguation systems. The first 2 that try to exactly match properties we extract from the 3 sources, Twitter, Wikipedia, and the web. And the last one that is a context-based approach, which try to disambiguate the entities by looking at the context. This one was previously published on this paper. So, as I said, at the end, we use a majority voting system between the 3 systems to select linked profile. Again, for the messages, as I told you, we search for sentence-specific keyword, and we extract link. We have the corresponding page from the platform. We find cues that we can match, for example, date, and title. We search on Wikipedia for this cue, for this keyword, and we do the match. And these are the 2-way round in order to find matches starting from Wikipedia or from Twitter. So the resources available, as well as the code we developed for the matching phase. What to say more? Okay, so at the end, we have a 90% precision for the mapping of people from following relation and 96% precision for the other interest. To conclude quickly, due to a variety of issues, the load ecosystem, lacks of social data, we presented a methodology which is able, with a minimal human supervision, to automatically extract and link the information that are social aware, and then we are now focusing to show the benefits of such data, at least for the recommendation system task. Thanks.
thank you, Stefano. Questions from the audience? So I will start with one. So you specifically extracted information in a specific time frame that today is already 1 year old, right? So stuff on social media get old quite fast.
Yeah,
so
of course.
Do you think that what is more important in your approach, the data set or the approach to produce the data set? Can you repeat, I suppose, the same approach?
The replicability of the approach is quite high because the entire pipeline takes 2 days.
Okay.
Considering also the human supervision, which is just check the threshold of the precision, which is not real time, obviously. There is the possibility to do incremental, so you just compute the delta, at least for certain entities that are arising. So the novelty part has to be mapped to the link open data. Another aspect, I want to say that also the link open data has this problem because when you map to Wikipedia, things are changing on both ways. So it's quite difficult also to replicate exactly the same execution of the pipeline. So this is an open problem. I just had time to write on bold on the one of the first slide. Other problems are related to the privacy, that policies changes many times during the year. So there are open issues on this specific task. So thanks for your question.